Hey everybody, hopefully by now you guys have this notes page out in front of you. We're going to use this page to take some notes. I'm going to show you what special cases look like in systems, especially by elimination. So we're going to work through a couple problems together. I'd like you guys to write down the notes that we take. And then we're going to look also what these special cases look like a graph. So I'm going to kind of show you what the expectation of the work is today. But hopefully by the end of the hour you guys have an idea of how to tell if there's no solutions or infinitely many solutions, not only from looking at the equation, but also looking at a graph. I'm going to try to work on 2 or 3 of these, then I'm going to let you guys finish up by finishing the rest of them. And then I would like you to turn this in, and I'll pass these back to you on Monday so you have these notes back. But I would like these turned in so I know that you guys are doing the right thing. Hopefully you guys have been doing the right thing, and you got your warm-up done, and everyone's in the right spot, and you guys are being respectful and responsible. So let's take a look at number 1. This system is set up for elimination. We have our x's right above our y's, or x's above x's, y's above y's, numbers above numbers. And so we have to look and try to just see what could possibly eliminate. When I look at this, I see a positive 15 here. So I know that it sure would be nice if there's a positive 15 here, that underneath it there would be a negative 15. And so what I'm thinking is, what could I do to this bottom equation to get a negative 15 in this spot right here? And remember, we're allowed to multiply because we could multiply by everything, keep everything equal. So if I want to multiply this 5 by something to get it to turn into a negative 15 so it would eliminate with that 15, I'm going to multiply by negative 3. I'm going to multiply by a 3 so it gives me a 15. I'm going to multiply by a negative 3 because that would give me a negative 15. So we're going to take this equation here, we're going to multiply everything by negative 3. And so we would get negative 15x minus 24y equals negative 21. And again, all I did is I took negative 3, multiplied it by 5, took negative 3, multiplied it by 8, and took negative 3 and multiplied it by 7. And I got all those numbers there. The top equation doesn't have to change, so I can just rewrite it. 15x plus 24y equals 16. And now I can do my elimination. And this is probably where you can already start to see that, yeah, there's something that's going to happen that hasn't happened before. As I go to add these straight down, I notice that my x's cancel out and my y's cancel out. 15 minus 15 is 0. 24 minus 24 is 0. So there's nothing over here. And then on this side, I got 16 minus 21, which in this case is negative 5. Since there's nothing over here, I'm going to put that 0 there. And we've already looked at lots of equations where this happened, where all the x's or all the y's canceled out. And the same exact reasoning we've had before is going to work here. That if all the x's and y's cancel, and so I'm just left with a statement, I have to decide if this statement's true or false. If the statement's true, then there's an infinitely many amount of solutions. If it's false, then there's no solutions. In this case, 0 is not equal to negative 5. That's a false statement. So what we would say is there is no solutions to this system. There is no x and y that work in both these equations. There is no solutions whatsoever. And sometimes that idea of no solutions is much easier to understand when we look at graph form. And so what I would like you guys to do today when you're working on these problems is not just do the no solutions, that's not too hard, but I would also like you to take a second just to kind of make a spot on your paper where we're going to look at what would the graph of these look like. And so if we just kind of make a graph over here, we can kind of get a sense of what the graph looks like. If you want today, you're more than welcome to do it, and that is to go to Desmos to graph these solutions. So if I just pop up Desmos here, and I'm just going to type in our 2 equations that we had to start with. So our system was 15x plus 24y equals 16. And the other equation was 5x plus 8y equals 7. What I want you to notice is what happens here when I zoom in. Remember, our answer is the one point where these 2 lines meet or intersect. Well, what do you notice is happening in this graph? Where do these 2 lines meet? If they're parallel like they are here, those 2 lines are never going to meet. And because they never meet, then we know there's no solution. And so this is what graphically no solution looks like. It just means lines that never, ever, ever meet. And so when we go to kind of set our graph here, you don't have to get an exact graph. I would just like you to kind of have a sense of a no solution graph would have parallel lines. And so when you finish these problems, I might have you make a graph, and that's what you'll kind of do is just decide what that graph looks like. Obviously, this isn't the exact spot of that graph. I don't think it had this x-intercept and y-intercept. I was just kind of freehand drawing the idea of what that special case looked like. All right, so let's look at one more. Maybe a third one. We'll kind of see what's time. Again, our goal, elimination, but also now we're looking at special cases. So let's take a look at number 2 and see where we go from there. Again, looking at this system, I know that I need to get my x's or y's to cancel out. I can look at either my x or my y. I'll look at my x's here. So if there's a negative 16x on top, then I got to think about what I'm going to want on the bottom. So if there's a negative 16 on top, I want a positive 16x on the bottom. I'm kind of thinking about this in my head, that this negative 8, it sure would be nice if it was a positive 16. Well, it's not a positive 16, but there is something I can do to this equation to make it a positive 16. And that is I can multiply everything in this equation by negative 2. Negative 2, because negative 2 times negative 8 would give me a positive 16. I need a negative times a negative to get me back to a positive. And so if I ever want to switch the signs, I got to multiply by a negative. Otherwise, it's not going to switch them out. So if I multiply the bottom equation by negative 2, then I get 16x there. Negative 2 times 8y would be negative 16y. And I do have to do negative 2 times 0. It's just that negative 2 times 0 just remains 0. So that's what the bottom equation is. The top equation, negative 16x, I don't have to change it. I can just take that equation and bring it over. Negative 16x plus 16y equals 0. And now I can do my combining of equations. I can just add this side to this, add this side to this, and just see what I get. So I get negative 16 and positive 16. They cancel out. And then I get this 16y and this negative 16y, and they also cancel out. And so what happens is I get 0 on this side, and 0 makes 0 on this side. So here, all my x's and y's canceled out just like before, but now I'm left with a true statement. In true statements, we usually say like all solutions are all real numbers. With systems, we're going to say there's infinitely many solutions. And I want to talk about why we use the word infinitely many versus all solutions. All solutions could work depending on what you mean by that, but most texts talk about this idea of infinitely many solutions. And I think the easiest way to figure out why they use that infinitely many is to look at the graph. So once again, I would like you just to go over to the side here. Hopefully you have room, but let's make a spot just to kind of put the graph of what infinitely many looks like. So we have our XY graph, if you want to put that in. While you're putting in your XY graph, I'm just going to go ahead and switch over to Desmos and show you what that looks like. So I have, for my first equation, I have negative 16x plus 16y equals 0. And then my second equation, I have negative 8x plus 8y equals 0. Now I want you to see what happens when I put the 0. Here's my first line. When I put in the second line, it changes color because what happens is my first line and my second line, if I click on each one, you can tell that those lines are the exact same line. So if I said, well, where's our answer? Our answer is any point where these two lines meet. Well, these two lines meet in all these different spots. So one of my answers could be 1.02, 1.02, or 1.13, 1.13. Every one of these points on this line, or this line, because it's the same line, any one of these points would work. And if I said, well, how many points does it share? They share an infinite amount of points. It doesn't mean that every solution works, though. If I look at this point right here, 0, 10, you can see 0, 10 is not on either of those lines. So 0, 10 would not be a solution. But any point that's on either one of these lines, because these lines are the same lines, any one of those lines, points on the lines would work. So when we talk about infinitely many solutions, we say it's infinitely many because not every solution, if I put x1, y1, sorry, x1, y1 would work. If I put x2, y5, 2, 5, that's not necessarily going to work. So we want to just make sure it's solutions that are on that line. So when I come back over and look at it, I would probably show this graph as a graph where both lines are on top of each other. And that's kind of hard to draw. Sometimes when you see it in drawings, they'll have the one line and then they'll have arrows a little bit shorter. So that way it's like, that's the same line, but that way you can tell them apart. So they'll kind of have two lines on the same one. And that's what infinitely many solutions would look like that way. So you could have no solutions, you could have infinitely many solutions, or you could have problems that just have one solution. And so there are some of those that have one solution as well. And that's the ones that we were talking about earlier. And so we'll just finish up here in the last 2 minutes, 3 minutes, just talking about this idea of if there's one solution. Then I'll let you finish the rest. So if we look at number 3, the last one, sorry I'm going so quick, but there's a 15-minute limit on these videos, so I got to finish up. I know that I got to get the x's or the y's to cancel. I notice an 8 I'm never going to cancel with a -9, and a -8's never going to cancel with a 6. So in my head I think, is there something I could turn both 8 and 9 into? And I know 8 times 9 is 72, so I could imagine the top being a 72x and the bottom being a -72x. And so what I'll do is I'll multiply each equation by the number that would allow me to get to 72. So if I want to get from 8 to 72, I'm going to multiply by 9. 9 times 8 would give me 72x. But to keep everything equal, I have to multiply every single piece of this equation. So I would multiply the y by 9, and I would multiply the 16 by 9. And so you're probably going to need your calculator for those. 16 times 9. You could probably do it mentally if you wanted. 16 times 10 is 160. You know, subtract out the 16 you're not using, and it would be 144. But I would use a calculator to do that math. And then I'm going to have to do the same thing with this bottom equation. If I want this bottom equation to turn into a -72, I'm going to have to multiply it by 8, because 8 times -9 is what would give me a -72. So if I do that, 8 times -9 is -72, 8 times 6 is a +48, and 8 times 12, or -12 in this case, would be a -96. Sorry about that. And so I could just go through and write those out. And then I would just add straight down from there. Again, if you want, just use a calculator to do these calculations. -72 and 48 would be a -24y. 144 minus 96 would be a 48. I don't believe there's any decimals today, so if you are getting decimals, you probably made a mistake in some of these calculations, so just be careful. Watch your positives and negatives, but from there you're just going to solve like normal. So I'll divide by -24, and I get y equals -2. Now remember, our final goal is to find the one x and y that makes both of them true. And so I'm going to have to plug this y value back in. If I plug it back into the top equation, 8x minus 8y equals 16, and I plug -2 into that y spot, I'll get 8x. A -2 times a -8 is going to give me a +16. If I subtract 16 from both sides, I'm going to get 8x equals 0. Divide by 8, and it looks like I get x equals 0. You can double check these. You could go to Desmos if you wanted. If we go to Desmos and type those in, hopefully they meet at 0, -2. And then if you go to make your drawing, because I'd like you to do that on all of these, just go ahead and make your drawing and just show 2 lines. You can use Desmos to help, but you know those 2 lines are going to meet at 0, -2. So if you just want to even kind of just get the idea of putting both lines in, I don't think that's where the lines are really at, but I just want you to know that sometimes they meet at one point, sometimes they're on top of each other, and sometimes they're parallel like this. You could use Desmos and get a more accurate graph. If I look at this, the x-intercept of this top one would be 2, the y-intercept would be -2, so it looks like it should have been more like that. And I could do the same thing for the other one. Alright, we're going to leave it there, and hopefully you guys made some sense of it, and I'll see you guys later.